Okay, good. There are 20 students right now. All right. So in the last lecture, I talked about the responsibilities of OS, and in the end, I mentioned that the OS also needs to like manage the free space, that how the free space is allocated and so on. And today we'll have like a more deeper look into it. And today's topic is going to be free space management, and it is done at two levels. So, at low level, managing the space in a processes heap, and at high level, the OS managing the physical memory. So, we'll see that why the difficulties arise is because of variable size requests. So, managing free space is easy when space is divided into equal chunks. But hard for variable size requests. So why it is easy when divided into equal chunks? Why do I say it's easy? Like what can be the strategy then?
Maybe because to check we can skip particular number of spots.
Yeah, and we can just maintain a list of whatever is free, and always, since it is going to be like fixed size, we can just allocate the first free one. We don't have to look, we don't have to worry about the size and so on, right? But these kind of hard things one has to take care, like for heap, because malloc you can ask for like variable size spaces, and for OS when trying to implement segmentation. Because last time we saw that segments can have like different sizes, right? And the problem that we are going to have in this, or the thing that the aim is to minimize external fragmentation. Okay. So what is the external fragmentation? When the free space is divided into small chunks. So even though memory might be available, or free memory, even though total free memory size is larger than the request, still we cannot fulfill the request because no contiguous like block of memory which is there for the request. So, so this is why fragmentation, because free space is divided into small chunks or fragmented. Okay, so let's see it with a small example. Suppose you have 30 bytes of memory and the first 10 bytes are free, the last 10 bytes are free, and this is used. And now suppose a request comes for 12 bytes and then it will have to fail. Why? Because you don't have 12 bytes anywhere contiguously. You have 10 bytes here, you have 10 bytes there. So total free space is 20 bytes. Okay. Good. So this is the like the basic setting where we will which we'll try to solve, and we'll see we'll concretize it more and see what we are going to do. So the basic question that we are going to address today is or questions, let's say. How to manage free space for variable size requests. What are the strategies? And what are the overheads? In terms of space, time, and this we would like to minimize the overheads. Right? Okay, good. So before we get into like doing some mechanisms and policies for free space management, let's start with some assumptions. That will be helpful in designing these mechanisms and these policies. So first is that we are going to use the malloc library for today's purpose. So what is the syntax? It's void. So what does malloc take? It takes size. So okay, why am I writing that? Takes just a moment. It's my internet. Okay, takes size as argument. Okay, and what does it return? It returns a void pointer to a region of that size. So we had discussed it earlier also, malloc and free. So what does free do? It just takes a pointer as parameter and frees the corresponding region. So as I had told earlier also, it does not take size as a parameter. So there should be some way of knowing how much memory to free. Okay. So these are the two functions, malloc and free. And we'll manage the heap using something called free list. And this is going to be a list of free regions. And we will only care about external fragmentation. So what is the difference between external and internal fragmentation? So internal can also occur. So what is internal fragmentation? Internal fragmentation happens when, so external fragmentation is whoever is allotting the memory or the space. Now it can see some free space which is not utilized and it cannot allot it, even though the total space might be there. In internal fragmentation, now some space is allotted to a process or to a function, or and it is being unused. It is being wasted by the function or by the process. So space allotted is not used, or more space is allotted than needed. So, but this will not worry about. We'll worry about only when the space allotted and the gaps between them, the fragmentation that arises because of that. Okay. And fifth, last time, if you remember, towards the end of the lecture, we looked at this concept of compaction, but we'll assume that no compaction of the heap will happen. So what does that mean? That when one address is given to the heap or one chunk of memory is from the heap is given to a function or process, then the heap or the memory manager that we are going to talk about is not going to move it around. It is going to stay at the same place. Memory chunk allotted will not be moved. By the library. And the final assumption is going to be the memory that is being managed is contiguous. Okay, so it might happen that a heap is broken down or a heap finishes its memory that was allotted to it, and now it has requested more memory, and the OS has given it the memory somewhere else, and so on. But let's assume that all the memory that is being managed for this lecture is going to be contiguous. Okay. So, any questions till now?
So we are looking at managing the space inside a heap of a process. Or
Yes, that's what we'll be looking at.
okay.
But similar strategies can be used by the OS also for implementing segmentation.
Right.
So as I said, there are like these two levels. One can be at the low level for a process that the free space in the heap has to be managed, and at the high level, the OS might have to do some memory management. But so we are going to look at the mechanisms and stuff for the heap, and then like you can extend it to the operating system level also. Okay, and here we can see some nitty-gritties of how the memory actually looks like and so on. Okay, good.
So in this context, what does external and internal fragmentation mean?
Okay, so all right, so let's just clarify that once. So external and internal fragmentation. So suppose this is the heap, and now the heap has allocated some space to some function here. So this space is allocated, and this space is allocated. This is free. Again, this space is allocated. So on. Free, free. So suppose 10 bytes is free in all, and now a request of 20 bytes comes, and the heap cannot allocate it. So this is external. Why? Because the heap has allocated these spaces, and in between there is free space that the heap now cannot allocate. Okay, so this is external fragmentation. And what is internal fragmentation? Now the heap has allocated these whatever initial bytes to something, but it is not using all of it. It is just using, okay, so this is used and this much is wasted inside, but it is inside what the malloc has allocated to a function or something. But the function is simply not using. So that's internal fragmentation in this context.
Yeah, got it. Thanks.
Okay. So now the mechanisms that we are going to look at are splitting and coalescing. So these are the basic mechanisms which will be important is in managing a free list. So let's start with the same example that we had earlier. That now suppose we have 10, 10, 10, and this is free, this is used, this is free, this is 0, 10, 20, 30. Okay. So now suppose we have the free list. It is going to have two elements or nodes. Okay, first one is going to have the start address of this. So let's just write it. So head, then it will have address 0, length 10 is free. Then add address 20, length 10 is free here, and then null. Okay, good. So this is how the free list looks like. Now suppose a request for anything greater than 10 bytes comes. So then it will fail, right? If equal to 10 bytes, then any of the free blocks will be allocated. But what to do when for requests of less than 10? Okay, so that's where this thing called splitting comes. So what will it do? Look at a chunk that can satisfy a request and split it into two. One to fulfill the request, and other remains on free list. So suppose in our example, 1 byte request comes. Then how the new free list will look like? First, it will look at this, suppose this one, and it is going to allocate space from here of 1 byte from the third chunk. So now the free list will look head address 0, length 10, address 21, length 9, and null. And this space has now been allocated. Okay. So it splits up into two parts. One, it allocates to the request, and the other one, it remains on the free list. Okay, good. Now, the other thing is coalescing. And so suppose again, this was the situation, the same earlier. Used free, and free 10 comes. So what does free 10 mean? Free 10 means that go here and like free the chunk of memory which starts at 10. Somehow we assume for now that the free function basically figures out how big is the chunk, and suppose it figures out, so here coincidentally they are both the same. This is size and not the sorry, this is the address and not the size of the chunk that is going to be free. Okay, so this is not the size. Okay, so suppose free 10 comes, then what is going to be the new, let's say, the free list. So it's going to be head, address 0, length 10, address 10, length 10, address 20, length 10, and null. Okay. Now the entire heap is free, but it is still divided into chunks, into small chunks of 10 bytes each. So even now, if some request comes of greater than 10 bytes, the memory allocator cannot allocate it memory, right? So So what should do? What should this coalescing thing do, or it does? So while freeing, also look at nearby regions. If they are free, combine them to make a larger chunk. So this is like very natural and obvious thing to do. It seems that okay. I mean, now this has been freed, the central one, and now the two beside it are also free. Then why keep it divided into these things? So now the new list will look like head, address 0, size 30. Okay. So this is just the basic, like in very simple terms, the what splitting and coalescing do. We'll see them in more detail about like when they are actually in the heap, then what happens and how do things work. Okay, but just to give a very basic and understanding of what splitting and coalescing do. Okay. Now there is one problem that we had was that for free, how do we track size of the allocated region? Okay. As like we saw that free does not take size parameter. Okay. So the malloc library should know. Should know how much stuff is being freed. And put it back into free list. Okay. So the one way to do this, to track how big a region is to use a header at the beginning of the section that is to be allocated. So right before region of memory that is going to be allocated. Place a header. And what the, like, what it contains. So basically what happens now that whenever malloc is called, when it returns the space, it also puts a header. So it looks for the space which is slightly larger. So suppose user calls malloc 20, let's say. Okay. And stores the pointer in PTR. Yeah. Any question? Okay. So the user calls the malloc function with the parameter 20 and stores the pointer that the malloc returns to a variable named, a pointer variable named PTR. Okay. Now, as I was saying, the header. So what does the header contain? So let's just define the header. It contains the size of the region and a magic number. Minimally, it can contain some other information also. But so this magic number is just to, like, it is throughout the process, it is going to be the same. And all the headers will contain the same magic number. So let's say it's going to be 9876543. Okay. So this is going to be the same for, like, throughout the program. And this is just for some sanity check that I'll come to, that if somebody is seeing this header, they can check that this is actually a header and not some other kind of memory. So this number should be something that is not used frequently by memory and so on. So that's why some, like, nice looking, but also a random number, not like 0 or 1 or something. Okay, so okay, so this is head. So header, let's see. Okay. So this is the structure of the header. So it contains two things. It contains the size and the magic number. And now the user has requested malloc 20. So it needs 20 bytes. So how will it look like in the memory? So initially it will be header. And it would have size, which would say 20. It would have magic number, which will be some 9876543. And then there will be 20 bytes of memory that is allocated. And this pointer that is going to be here at the start of the space that is going to be allocated. Okay, so this is how the malloc works. So just one thing to remember, that when looking for free space, malloc looks for space of size, not exactly what was requested, but request plus header size. Okay. So not just the request size, but request plus header size. So, and why request plus header size? Because the requested space is going to be needed by the program and the header will store the information. So it will put the header there, put the pointer after the header, and then it will give the space, give the pointer back to the program. Now, what happens when free comes? So now suppose comes free pointer. Okay, so free will get this pointer. Okay, but then the job of free is not that hard. So free will come here. So free will calculate. So let's say here is header pointer, HPTR. Okay, HPTR, and this is not very hard. Why? Because it knows pointer, it knows the size of the header, it can minus that, and it can calculate the location of the header pointer. Okay. Now check the size, check if it's actually the header using the magic number that, okay, it will just verify whether the magic number is the same. And then we'll put this whole block, it will free. And free header plus allocated memory. So let's say this was 8 bytes. If the header takes size 8 bytes, then total it will free is 28 bytes. Let's say this was if header has size 8, like 4 bytes for the integer size and 4 bytes for the pointer. Let's say. Yeah. Okay. So is that clear that whenever we call malloc, the function looks for memory that is size of what is requested plus the header size. And whenever we call free, free will go there, look at the pointer, go up, look at the header, and then from the header, it will see the size that it needs to free, and it will allocate, it will calculate the header pointer, and from there, it will free the whole space of the header plus whatever was allocated. Okay? Good. Now there is another problem is where do we keep this free list? So a free list for the processes library, like so this free list is about the memory of the process which is there in the heap and so on. So where should we or can we keep it? Because this is also a data structure, this also requires memory. So where should it be kept? Any ideas, guesses? I mean,
Can be kept at the like every node can be kept at the beginning of the free space. Like
so free space meaning the heap or
so the free space, like inside the heap, there are several free spaces, right? So the beginning few parts of it can be used to say that this much size is free, and
yes.
then we can keep jumping.
Yeah, just like there is a small point that we are trying to manage the free space, but also we have to like manage the free space while being in the free space. So this data structure of the free list will also be inside the heap. So that is the point, and then it will have to like consider its size itself as well while managing the free space. Okay, and it has to keep updating itself. Yeah. Any question, Arpit?
No, sir.
Okay, good. So we'll see it like with like some example. So let's say that we have heap of 32 kbs or 4 kb size. So 4096 bytes. Okay. So initially, what should be the elements of the free list? Should have just one entry, right? For entire region. So let's define what the structure of the node of this free list looks like. So the node is basically like any node in the linked list, and it is just going to have, instead of the integer, it's going to have the size, and then it is going to have another pointer to the next node. So next is the next node, and that's it. So this is the size of that chunk, and this is pointed to the next node.
Shouldn't it also have the initial address of the free space?
So initial address of the free space will be just once. So that will be just so this is one node in the space.
No, I mean there is some chunk, so there should also be the where does the chunk start from?
Where does the chunk start from? So that will start directly after the list. So we'll see how it.
Okay.
Yeah. So right after when this node will finish, the chunk will start. So that's implicit in a way. Okay, good. So yeah, so we started with heap of size, let's say 4 kb, and now the list should contain one entry, but what should be the size of that entry? Okay, sorry. So what should be size of that entry? The size of that entry should be 4096 minus size of the node, right? So let's say this is also 8 bytes. So this is like 4096 minus 8 is equal to 4088. Okay, bytes. And so now what is going to be the free list? So it will sit at, so this will be the head of the free list, which is right at, so let's say the virtual address of this is 16 kb. because it has to be at some virtual address, right? So we don't need it right now, but we'll come back to it later. So this is the head, and there is just one node which says size is equal to 4088, and next is null. Okay, good. Now suppose a request comes for 100 bytes. Okay, then since there is only one chunk, the manager will now perform a split operation. It will split this into two. Now, while splitting this into two, it will make space for the header and so on. So what will it look like now? So now this space is going to be used, the initial bytes that were there. So it will be used for the header of the, so now it will have size is equal to 100, magic is equal to whatever 9 to 3, and then 100 bytes. And now the list, the only node in the list will be here. Size is going to be 100 plus 8 is gone. So this is total 108 bytes. So size is 4096 minus 108. So this is going to be 3980. No, and also 8 bytes for this. So this is minus 108 minus 8. So this is 3980. And then this will have next equal to null. Okay, so what did it do? When a request came, it divided the memory chunk into two, and it stored the header, and it gave the, and what is the pointer? Where is the pointer pointing now? So the head of the list will point here, and the pointer to the free space that the malloc will return will be here. This is the pointer, and this is the head of the list. Okay. So now whenever somebody is looking for space, they'll come to the head of the list and see that, okay, there is only one chunk because the next pointer is null and it has so much space available. And then, whether it can be allocated or not. Okay. So any questions about this? So you see, I mean, why the magic number is there is because like sometimes these locations, whether it belongs to a header or it belongs to actually a node of the free list and so on, might get like, a bit muddy, the whole distinction. So just to, for a sanity check, some number is kept there. Okay, good. So let's just continue further and let's say that another request comes of 100 bytes. Or let's say 3 requests come. Total of 100 bytes each. So it's going to be simple for now. So this will be just the size, 100, magic, then 100 bytes, then again size. So this process will repeat 3 times. And then we'll have now the header of the linked list will be here. It will have size, whatever is left. And if you calculate it, it's going to be 4088 minus 108 times 3 equal to 3764. So this would have 3764. Its next is going to be null. And then this is the 3764 bytes which are free. And while allocating, it will give these pointers. So let's say pointer 1, pointer 2, and pointer 3. Okay. So till now, nothing much interesting has been happening. It has been just allocating space and putting the headers for the allocated space and returning the pointers. So let's see what now happens when the second region becomes free. So a request comes which says free pointer 2. Then how will it look? Okay, so the first one will stay there. Nothing has happened to it. So size 100. Here will be the magic number, whatever it is. And then there will be 100 bytes which were allocated to it. And now the second one is free. Okay, let me just. So as we had said earlier, whenever free call is made, it will go there to the pointer, find out the header, look at the size, add the header size to the free region size, and free those many bytes and put that back on the linked list. So what does it mean to put it back on the linked list? It will make a node here. It will say size, again 100. So this is by coincidence because the size of the node of the linked list and the size of the header are equal here. But if they were unequal, then it will decrease by, so it will be 108 basically minus headers, the node size. Where the node is of the list. Okay. So the node of the list here contains size and a pointer. And now the pointer, so suppose we are inserting, so if you have done data structures course, in the linked list, you insert at the, like you can insert at like, if you have doubly linked list and so on. But you insert at the head. So suppose we are inserting here at the head. So the head will come here now of the linked list. It will point here. And the next will be the previous pointer. So earlier, that's why I was saying that suppose this was 16 KB. So now the next is going to be 16 KB plus this size, all this. So let's say 16708. Because 16K is going to be whatever, and then if you do the calculation, then yeah. So basically it points to the next one. And this is going to be size 100. And then we have size and magic for the third block, which is still in use. So let's say this small region is 100 bytes. And so pointer 1 is still there. Sorry, not that. Pointer 1 is still there. Pointer 3 is still there. And now then there is this next node, okay, sorry, of the list, which says here now size remains the same, 3764, and then next is null. And this address is actually of this location. So now when somebody starts looking for some address, it goes to the head, then sees whether this satisfies or not, or whether they want to allocate from here. If not, they go to the next, and they go to the next, and so on. Okay. Now, suppose this one also gets freed. Now, suppose free pointer 3 also happens. Okay. And then how will it look like? Then there will be this first the header and the space. So again, size, magic. Okay, I should have made something bigger. Then the 100 bytes there. Now the head was here, but now, okay, so let's do this. So this is says size 100. Next was at 16 something, which was pointing to the, so this was, okay, this was 100 bytes. This was something, this was 100 bytes. This was the final. Here the next was null. Size is 4764, let's say 3764. Okay, so this one was pointing here, right? Now this one also becomes free. So size 100. Next is going to be whatever 16492, which is address of this guy, and the head of the linked list will be here, because now we have inserted this node. Okay, so this is how it looks. But now you see the problem, right? That I mean, there are these 3 chunks. They all have, like, small sizes, and they are contiguous. So what we should do, we should coalesce. So then what the memory will look like is just one chunk of memory, that is then just one. Next is null, and the whole space is. Okay. So is the mechanism clear? That how this list is embedded inside the heap itself, and how it manages the space using the sizes. Any questions? Okay. All right. If no questions, then we can go ahead. So there's another thing that what if the heap runs out of space? Then there are 2 things. One is just to fail. Just say that, I mean, okay, we have run out of space. But what happens is that many memory managers start with small heap, and request OS for more memory when they run out of space. What OS will do? OS will assign some physical memory block and map it back to the process's address space. And now the memory allocator can happily think that the heap is bigger and grant the request. Okay, so this is just for what happens when the heap runs out of space. Okay, now we are going to talk about some strategies for how to allocate the free space. So suppose some request comes. Now, which block you are going to allocate? Are you going to just give the first block, or you are going to look for some suitable block? What is going to be the suitable thing, and so on. Okay, but while doing that, we are going to have two aims. First is going to be it should be fast, and second, it should have less fragmentation. Okay, and fragmentation will happen because the requests are of arbitrary size, so there is no best way, and every strategy will have its pros and cons. But let's just go through them quickly. That which are so one is called best fit. So what is best fit? Best fit looks for all blocks of size greater than or equal to the request and allocates the smallest among them. Okay. So this, what is the intuition? Good fit, so less wasted space. So one pass, it would take one pass through the whole list to allocate. Okay. And so one pass through the whole list. So this is slow because the list can be very long. And you have to, for every request, you have to search the whole list. So this is called best fit. The second one is called worst fit. Again, looks for all blocks of size which are greater than or equal to the request and allocates the biggest among them. What is the intuition for this? Any guesses? Why would you like to give the bigger ones? Okay. Nobody's saying anything. So you have many blocks of memory. So one is free here, one is free here, one is free here. Suppose the bigger one is free here. So these ones are free. And what the best fit does, so suppose you got a request of, so suppose this was 10, 20, 30, and suppose you get for 12 bytes, then what will the best fit return? Best fit will return this 20 size block, and worst fit will return this 30 size block. So can you see the intuition now?
Yes, sir.
So the intuition is bigger blocks of memory will be available, because after there will be 18 size here, and here will be just 8 size. If in case of best fit, there will be just 8 size block, which will not be of any use. And for worst fit, it will be 10, 20, and 18. So it tries to do this. Again, but you can come up with something, some like input for which the best fit will perform better, worst fit will not perform better. So these are just like different strategies. Again, would take one pass through the whole list. So slow. Okay, good. So now to get rid of this slow part, what we do is called first fit. Okay. So what is first fit? Assign the first block that is greater than or equal to the request. This is fast, but populates the list at the beginning with small blocks. So then, like, everything else you have to search, like, till later. So there is first fit, and then there is thing called next fit, which is just a modification of first fit. So to rectify this, keep a pointer to last location where we looked for space and start the search from there next time. So again, like this is similarly fast as first fit because you like your pointer is at some location and you just start the search and whatever after that is first you allocate that, but it distributes things comparatively more uniformly. Yes. Any question? Okay, so these are the four like very basic and very simple strategies: first fit, best fit, worst fit, first fit, and next fit. There are some other approaches also. So two of them I'll discuss in like 5 minutes each, let's say. So one is segregated list. So here, suppose one kind of space gets asked again and again. Okay. If an application has many requests of same size, then a separate list can be kept for these requests. And for other requests, the normal memory allocator, whatever is there, will work. So the advantage is that fast for those requests and less fragmentation because now you have these fixed size. Complication, like how much memory to keep for these lists and so on. What to do if we have kept some memory and it is not being used, how do we take it back, how does the memory allocator take it back, or what happens when we need more memory. So then this is called the slab allocator, and it is a very popular thing which was designed. So you can read more about it, but the basic idea is that if there is some request that is coming again and again, for example, in OS at boot time, the kernel initializes lists for locks, file inodes, etc. Because these have a fixed structure, so they are going to have a fixed length. So then you can just have a list of them, a list for these things separately, right? Good. So now the next one, which is a nice one, is called buddy allocation. Okay. So this looks at the free memory as a big chunk of size 2 to the n for some number n, right? Now, when a request for memory comes, then search for free space recursively, dividing the free space by 2. Till we reach right size. What is right size? Dividing further will make the block smaller than the request. And allocate it. Okay, so search for it and allocate like this. So suppose you had whatever, 64 KB, you divide into 2 parts of 32 each. Then you look here, now you have 16. Oh, suppose you look here, 8 and 8, and suppose the request was 7 KB, then you suppose allocated this block. Okay. So just to see from this example that some internal fragmentation happens. Because always gives space in power of 2. So if the request is smaller, then it will be allotted more space and it will go wasted. Okay. So suppose here the first block is given. All right. Now the good thing about this buddy allocation is that when freeing this block, what will the the manager do? So the allocator looks at the buddy of the block. So who is the buddy? The buddy is this guy. Of this block, this is the buddy. Is free. If so, coalesce them to make bigger block. Now again repeat the same thing for the other level. Now look at body of bigger block. So now you suppose this was free. So this 16 one is there. Now its body is this other 16 one. Look whether it is free. If free, coalesce and make a bigger block to be free, and continue this till a block or a body is found that is not free, or you free up entire memory. Okay, so this is the strategy for body allocating. And why it works well is because, so the key fact here is that if you look at the memory now is getting divided into two. So if you look at the addresses of any bytes here and here, so this address and this address will differ by just one bit, which is going to be the MSB in this case. But here now they'll differ somewhere else. This 16 and these 16, these will also differ by just one bit, and that will be the second bit, and so on. So the buddies differ by just one bit. And how is that decided? That which bit? Decided by which level, okay, of the tree we are at. So now looking for the buddy becomes very simple because now you have one block, you want to find its buddy is free, so you want its address, and the address is just changed one bit. You go to that address and see whether it's free or not, so it's really fast. Okay, good. So this is the buddy allocation and how it works. So the basic idea is that if you have a 2 to the something size address, and then you have these addresses written down, then if you write it down, you'll see. So this is like you can try for yourself to see that these addresses differ by just one bit of the buddies. Okay, good. Now there are some other ideas also, like so here we use like linked list. So search is slow. So if we have many nodes, then this might be very bad. So to counter this, many other data structures are used, like balanced binary trees or split tree, etc. Okay. So, and also like for multiprocessor systems, so we want managers that work well on multiprocessor systems, and which might look very different from a simple manager that like looks on a single processor system and so on. So these are just like, just to give a flavor of like, what other things can be there. You might have seen like balanced binary trees and split trees in a data structures course, and how the operations are faster there of searching especially. And yeah, so that is today's lecture. It's a bit over time, but are there any questions? Yeah.
So in case of free,
Mm-hmm.
we always pass the pointer that points to the starting address, or we can also pass any other position, right?
No, you pass the pointer that has been returned by malloc.
Okay, so we can't do something like ptr plus plus and pass that.
No.
Okay. Okay.
Any other question?
Sir, sir, can we get some kind of practice problems or something so that we have some idea of what
I mean,
kind
there
of
is
question?
not much. So whatever has been taught, like if you understand well, you are going to be fine in the exam. Don't take too much that okay practice problems or whatever. It will be a 1.5 hour thing, so it will not be something. It will be proctored, so you will have to keep your videos on, and so you will be sent detailed instructions for that. And since this stuff is very basic and you can find it anywhere, so that's why I want to keep it proctored. And yeah, I don't think I'll be making a practice test because it's not going to be very exotic anyway. The exam, it's going to be a very normal thing. Yeah. Harsh, you're saying something?
No, sir.
Okay. Your mic was unmuted, so I thought. Yeah. So it's just go through the stuff that has been taught. There are the book is there, which has all the stuff. You can rewatch the lectures, and if you understand everything, I think you should be fine. Okay. So good luck for the minors. Yeah. Say.
Yes, can you give an idea about the pattern of the paper?
Pattern of the paper, there will be 4 or 5 questions, descriptive but not too long, and something that you'll be able to do in 1.5 hours, definitely.
Okay, sir.
Yeah. So they'll be mostly descriptive. I might include something about coding, but let's see. Basically, it is going to be what has been taught only. Okay.
Okay, sir. Thank you.
Okay, good. So thank you everyone, and good luck for the whole minor week and the exams. Okay. Thank you. So I'll send the instructions about it on email or yeah. So it will be in the slot which is there, 10 to 12:30. So yeah, 10 to 12, let's say. And yeah, so you'll be divided into groups or something. And so I'll send the detailed instructions. Okay.
Okay, sir.
Thank you.